Hey. So in this video, we are going to be talking about an introductory idea from physics called work. Now, work is typically given because it's one of the nicer computational applications of calculus outside of the mathematics world. However, because we are in a mathematics-based video, we're going to be talking about the math behind this. If you would like to know a little bit more about how work actually works, then I would definitely recommend going through and trying to find this concept in a physics text or through a physics video. But let's actually talk about the math behind it. So let's jump into this exploration. Let's suppose we have a constant force, and this force is being exerted on some sort of an object to move it in a straight line. Then this force being exerted on the object has an amount of force, as well as a direction of the force. So these two words are italicized because they're actually really, really important quantities. If you have a quantity that has an amount as well as a direction, then from what we've now seen from previous videos, we have a vector. Vectors are quantities that have both size and direction. In this case, size means how much of something is there. And in this case, we measure the size of the force as an amount. We'll be talking about how to measure these and what units these look like pretty soon. But for now, we just really want to notice that force has an amount as well as a direction, which means that force can be represented by a vector. So let's do so. Let's suppose that we have a force called capital F, and this force is being exerted on an object to move it in a straight line, but this force is not necessarily being exerted in the exact same direction as the object is moving. Now, we've seen this several times in reality. If we, for example, have a box right here, and this box is sitting on this flat ground, and we are trying to pull this box in this particular direction, then we sometimes might just affix maybe a rope or something around the box, and this rope would travel up in this direction. And we might actually have someone that's trying to pull this rope, and they're working really hard. Here's our person, and I know this person's not drawn really proportionally, but I'm trying. So we have this person, and they're pulling this box, and it's moving this box in this particular direction. Now the force is being moved along this rope. It's being actually pulled upward a little bit. It's definitely not being pulled this way. It's being pulled upward, and the box is not necessarily moving upward. The box is moving to the right rather than diagonally up and to the right. So here's an example of an object that has a force being exerted on it to move it in a straight line, but it's actually not being moved in the exact same direction as the force is moving. So I'm going to erase my masterpiece now. There we go. Sorry, I know it just would have been so distracting to look at that beautiful picture, but we need a little bit of the space. So here we go. We have a force F. It's being exerted on an object to move it in a particular direction. That direction might not necessarily be in the same direction as the force. So let's say we have an object, and it's moving from an initial point A. So here's A. And it's being moved to a terminal point C. Here's C way over here on the right. Then we're trying to move this object from the left to the right. There's our arrow. Then we can actually represent this motion with a displacement vector. This displacement vector we can give a name. We will call it D. So this vector D is the vector that starts at A and goes all the way to C. There is an arrow drawn here, so I'm going to go ahead and erase these blue marks. D is the directed vector from A to C. So we now have two vectors here. A vector AC, which is D, and a vector F. And we have an angle between these two vectors, but we don't really have a right triangle between D and F, but we do have a right triangle from AB to F. So let's actually consider the right triangle formed by the directed vector AB, the vector F, and then we can draw up a hypotenuse or sorry, not a hypotenuse, drop a leg down from the top of F down to B. When we do this, we are constructing a right triangle. Because we have an angle theta here, we can actually observe that cosine of theta is really the size of AB over the size of F. So if cosine of theta is the size of AB over the size of F, then we can actually multiply both sides of this equation by the size of F, and we get that the magnitude of F multiplied by the cosine of theta, that's actually the same as the magnitude of AB. Now from physics, turns out we're borrowing this definition, as we mentioned, from physics. The work done by a vector F is defined to be the product of the magnitude of the displacement with the magnitude of the applied force in the direction of the motion, in this case, that's AB. Those are a lot of words, so hopefully we can see here we have the magnitude of the displacement, that's the size of D, and the magnitude of, we're looking at the applied force in the direction of the motion. So we aren't looking at the force in its pure direction, going this way, but we're actually breaking this down into, if you pull something up and to the right, then you're actually pulling it partially in the direction going to the right. So we're just looking at how much of the force is going to the right. Well, that's this particular vector from A to B. So we have the product of the size of D with the product of the size of AB. That's what work is. So work is the size of D multiplied by the size of AB. Now, B isn't usually specifically given, so we don't really want to work with B or any quantity that involves B. But from what we've seen, the size of AB is the same as the size of F multiplied by the cosine of theta. So we make that substitution in right here. And these are now just numbers. The size of D is a number. The size of F is a number. Cosine of theta is a number, so we can use the associative property, and we can get rid of those parentheses. But this quantity is known to us. This is the dot product. This is the dot product of two vectors by looking at the size of the first vector multiplied by the size of the second vector multiplied by the angle between those vectors. So the dot product of D with F is the same as the size of D multiplied by the size of F multiplied by cosine of theta, where theta is the smallest angle between D and F. So we've just worked out a mathematical definition. From physics, we have this kind of long, complicated definition. I missed a lot here. Here's the physics definition, and now here's our math definition. The work done by a force F on an object whose displacement vector is D is the dot product of F with D, which you can look at as a dot product of F with D, or as the size of F multiplied by the size of D multiplied by cosine of theta, where theta is the angle between D and F. Two different ways to look at this. This is really as far as we're going to go with work. We're going to go through a couple examples, but we do want to do a typical unit study because now we're in some kind of unfamiliar territory in terms of what we deal with in day-to-day life. We don't often talk about force and work. We talk about displacement quite a bit, but let's just look at some of the units. Force is typically measured in pounds, which can be written with lbs. This is the United States units, or if you're in the metric system, then you're going to measure force with newtons, which is written with a capital N. Displacement is typically measured in feet in the US, or in meters in the metric system. And work is typically measured in foot-pounds in the United States. I know it sounds silly, but it is foot-pounds. Or in joules, which is a capital J, in the metric system. Now this is actually pretty important to point out which units we're utilizing because these units all work together. Work is measured as a product of force and displacement, so the units are going to be multiplied together, so they have to be compatible, which is why in the United States, work is a product of displacement and force, so it just has a unit of multiplying these two different types of measurements together. But if you are measuring displacement in, say, yards, then you're actually going to have to do a little bit of work to convert your units so that you're going to end up getting foot-pounds rather than yard-pounds or something else. Or if you're in the metric system and you decide you're going to be measuring displacement with kilometers or nanometers, then if you want joules, you're going to have to actually convert some of your units so that they actually match up. So it's pretty important to work out. All right, let's try an example. We have a rolling backpack, and this rolling backpack is being pulled a distance of 20 meters along a horizontal path by a constant force of 50 newtons. Now, before I even finish reading this, I'm already starting to build a picture in my head. So I have this person. I know you've already seen how great of an artist I am. Let's have this stick figure person. I don't even know where that line came from. Stick figure person, and they're pulling this rolling backpack. Let's make a little black wheel here. 2 black wheels. It looks like they're trying to hail a cab. It almost looks like a suitcase. Who knows? They have this, and they're pulling it along a straight path. Should be horizontal. I'm going to try to make it a little bit more horizontal, which means that person needs slightly longer legs. There we go. And this person is moving in this direction. So, they're pulling it with a constant force of 50 newtons, and they're pulling the backpack a distance of 20 meters along this horizontal path. So 20 meters from the beginning point to the ending point. We'll say here's 20 meters, and the force, I don't know, the force is 50 newtons. That's a measurement of how much force there is. So we know that the force is measured in 50 newtons. All right, so if we continue reading, it says the handle of the backpack is held at an angle of 55 degrees above the horizontal. So this angle right here, theta, is 55 degrees. Then it says, let's find the work done by the force rounded to the nearest joule. All right, so we have a few different quantities here. First of all, we have a force quantity, and what we know about work is that work is force dot product with distance. But we also know that there's another way that we can think of this. We can think of the work as being the size of the force multiplied by the size of the distance multiplied by cosine of theta. Now, with each one of your work problems, you want to start thinking about what kind of quantities do you have? Do you have a force vector? Do you have a displacement vector? Or do you have sizes? In this case, we have sizes. I know that this backpack is being pulled 20 meters. That's an amount. That's an amount of our displacement. It's moving 20 meters. It's being pulled with a force of 50 newtons, so that's a size of a force. We also know the angle between the displacement and the force, that's 55 degrees. So we actually have enough, not really to utilize this one, but we have enough to utilize this second formula. Work is the size of the force, which was 50, and this is measured in newtons, multiplied by the displacement, which is 20, and this is measured in meters, multiplied by cosine of 55 degrees. That's the angle between these two. Now, we didn't really cover it up here, but a joule is actually a newton being multiplied by a meter. So one thing that I know a lot of mathematicians like to do, especially me, is really study the units. I have 50, which represents the amount of newtons. I have 20, which represents the amount of meters. And the cosine of 55 degrees, that's a unitless number. It's just a cosine of 55 degrees. It doesn't have any units associated with it. So I really do have joules here. Everything is written here, everything is represented, so we can really just carry out the computations. Work is 50 times 20, so that's going to be 1,000 multiplied by cosine of 55 degrees. Now this says that we want to find the work rounded to the nearest joule, so we do want to carry out this computation. This is a nice exact value. Work is 1,000 cosine of 55 degrees joules, but we actually want to round this. Now, when we round this, we get 1,000 multiplied by whatever cosine of 55 degrees is. I have a calculator next to me. It turns out this is about 0.573576. It goes on, but there's a nice approximation. When we multiply by 1,000, we're simply moving this decimal 3 to the right, so we get 573.576, but it does say round this to the nearest joule, so this is about 574 joules. Make sure, I know you're doing you're doing physics problems, you're doing vector problems. You probably are familiar with making sure that you are in degree mode versus radian mode if you're typing this into a calculator, but I just want to point out, please be careful, make sure that you are using the correct mode in your calculator. We should just lastly finish this off because our problem does have some context. Let's actually give a response in context. Find the work done by the force. There is about 574 joules of work done by the force in moving that backpack. And there we go. So, biggest suggestion that I can give you in this case is start off by making sure that you understand this situation. Draw a picture, no matter how silly it looks. You can even take some time, decorate your picture. Here's a nice happy person pulling this nice rolly backpack. They are waving hi. Hello. Good job. Alright, take a few moments. Pause this video here and try this exercise. Alright, let's see what we've got. So it says a force given by a vector F, which is written out in terms of I, j, and k. And this force moves a particle from this point at -1, -1, -1 to a point at 1, 6, 0. So we have this 3-space example. Let's go ahead and draw some axes just to get a picture of this situation. Let's make sure to label our axes. Here's my x-axis, here's my y-axis, and here's my z-axis, all the positive parts of the axes. We have a point at -1, -1, -1. So here's -1 in the x direction, here's -1 in the y direction. Looks like they're kind of meeting around here. And then we're going 1 downward. So we're going down about this far. Here's this point. And this is the point at P, I think. Here's the point P. Let's make this a different color. Here's the point P. P is at -1, -1, -1. Q is at 1, 6, 0. So here's 1 in the x direction. 1, 2, 3, 4, 5, 6 in the y direction. And that puts us around right here. And then it's not going up or down at all. It's just sitting right here. Here's Q. This is at 1, 6, 0. So, we have a force, F, that is pointing in the direction of -2, 0, 4. Just write this out in component form. F is -2, 0, 4. And it's moving the particle from P to Q. This particle moving in this direction. find the work done by the force on the particle. Then let's actually find the angle between the force and displacement vectors. So here we actually have components. If we're looking at the two different ways that we can express force, or work rather, work is force dotted with displacement, or work is the size of the force multiplied by the size of the displacement multiplied by cosine of the angle between them. In this case, we don't immediately know the size of the force. We could compute it, but we don't know it immediately. We don't know the size of the displacement. Again, we can compute it, but we don't know it immediately. And we don't know what theta is. Again, we could compute it, and we actually will compute it, but we don't know it immediately. So this second equation, it works, pun intended, but it's not great. On the other hand, we have an expression for the component form of force, and we have enough that we can get the component form of our displacement vector. If d is the displacement from P to Q, then d is going to have components. The first component of Q minus the first component of P, so it's going to be 1 minus negative 1, which is 2. The second component of Q minus the second component of P, so 6 minus negative 1 is 7. And the last component of Q minus the last component of P, 0 minus negative 1, that's 1. So, we actually have the two vectors that we're looking for. Work is force dotted with displacement. And force we know is negative 2, 0, 4. Displacement we now know is 2, 7, 1. And we should be able to compute these. Dot product here says let's multiply negative 2 with 2. And then multiply 0 with 7. And then multiply 4 with 1. And add up all those results. It looks like here we get negative 2 times 2, which is negative 4, plus 0, plus 4 times 1, which is 4. We get 0. So, the work done by the force in moving this particle is actually 0. This force has absolutely no effect on this particle's motion. If this particle is moving from P to Q, then this force is not what's actually helping it move from P to Q. And that's actually something that we can state. The force, well, this is a question about work, so let's actually say something about work. There is no work done by the force in moving the particle from P to Q. There may be other forces at play here, but this particular force is not doing anything. That says let's also find the angle between the force and displacement vectors. Well, now we know that the work is 0. We can actually use this formula. So let's go back to that formula, and well, now we know that work is 0. We can find the size of the force. The size of the force we can find by coming over here to this force vector and saying the size of the force is the square root of the sums of the squares. So the square of negative 2 plus the square of 0 plus the square of 4. This gives us the square root of 32, which is 4 root 2. So over here we can say the size of the force is 4 root 2. The size of the displacement, well, the displacement is 271, so this means that the size of the displacement is the square root of 2 squared plus 7 squared plus 1 squared, which gives us a square root of 4 plus 49 plus 1, which is the square root of 54. Now 54 is 9 times 6, so this tells us that root 54 is the same as root 9 times 6, which means that this is the same as 3 root 6. Coming way over here, we can put that here as the size of D is 3 root 6. Lastly, we don't know what cosine of theta is. That's what we're actually trying to find out. So 0 happens to be 12 root 12 times cosine of theta. And I'm not worried too much about rationalizing this at all or about simplifying this at all. If we divide both sides by 12 root 12, then we actually get 0 is cosine of theta. Now, 0 is the same as cosine of theta when theta is pi over 2 or 3 pi over 2 or 5 pi over 2, etc. Could be in the other direction as well. But we always say that we want the smallest angle between them. That's what theta represents. The smallest of these that's positive is pi over 2. So, the angle between these two vectors is pi over 2. The angle between F and D is pi over 2. Or if you want in degrees, that's 90 degrees. Alright, this is actually a pretty important observation. If we go back to our discussion about orthogonal, then we actually know that the dot product of two vectors that are orthogonal is 0. So this says that these two vectors are orthogonal. The force vector and the displacement vector are orthogonal. When we have a force that is orthogonal to a displacement, that means that the work done by the force on the displacement of whatever, or on the object that is being displaced, that work is always going to be 0. In this case, the 0 does have units. We were in, where were we? We actually didn't have units in this particular case. But here we go.